Well, good morning, everybody. You know, I'm a little bit worried with Brian. As a professor, I'm used to talking in lectures for an hour and a half to 2 hours. If you see me looking down, I'll just be trying to see where the trapdoor is that Brian has the button for. All right, my name's Maurice Clark. I'm based at Texas Tech University. And what I'm going to be talking about today is the first attempts that I've been making at trying to model the three-dimensional shapes of asteroids. The picture I've got in the background there is the main telescope we have at Texas Tech. It's a very nice 20-inch plane wave, and it's actually had the family treasurer really worried since I've started playing with that. She knows when I retire in a couple of years' time and go back to Australia, what I'm going to be wanting to carry back with me. There's going to be an awful lot of SPUs involved in that one. Okay, so I've been doing asteroid light curves for probably about 10 years now. I've got well over 100 asteroid light curves, and it's been fun, but I was trying to think of what can I do as a follow-up to this. And then Brian has had his LC invert program that will let you take light curves and invert them and turn them into a three-dimensional model. So I thought, well, let's go ahead and try this. So the problem was I had to try and work out which asteroids to try and do. So I eventually used 3 asteroids. When the third one comes up, thank you. 3 asteroids in this program. What I had to try and choose them with was how good was my previous light curves. If any of you have been involved in doing asteroid light curves, sometimes you get a really nice clear curve. More normally, they tend to be really noisy and messy. So that was the first criteria to look at, was what were the really good clear light curves to use. Then whereabouts were they in the sky? Quite a few of them happened to be either in Cygnus or Sagittarius. Wonderful spots to do asteroid photometry on with all that lovely background star fields. And then how bright was the asteroid? Some of them were down around 18/19th magnitude, which tends to get a little bit noisy on the photometry. So we wound up with these 3, 1708 Pollet, which I'd have previously observed in 2005, 2036 Shergill, which I'd done in 2003 and also 2010, and then Candy 3015, also done in 2005. So here's the data that I got for Pollet. On the right there, we've got the data from 2005, and on the left is the data from late 2011, where I made the next set of observations. Periods that I derived came out to be nice and close to each other, which was always good to see. As well as the general light curve, there are some differences, which is what we would hope for, because that's what we'd need if we're going to try and model the shape. We want to see some differences because now we're in a different part of the orbit of the asteroid around the Sun. So the next step then was to use Brian Warner's LC invert to try and invert these light curves into making out a shape model. First thing we do is run it through the software, which is still very much a black box to me at the moment, trying to work out how it works. But we wind up trying to get a sidereal period for the asteroid instead of synodic. And then once we get that done, we run it through another routine in the software where we're trying to work out in which direction could the pole of the asteroid be pointing. And we get a map such as this one here. Come on, thank you. In this one here, the dark blue represents the minimum error between a possible model and the data that we get. There are 2 fairly nice solutions in here, with the darkest blue 180 degrees apart. This is fairly typical, I'm led to believe, with asteroids which have got a fairly low inclination. And so you've got to try and decide, well, which one of these is more reliable than the other one. But at least we've got two concentrations of dark blue, so this is nice. This is what we like to see. We then have to then turn around and, using these two possible pole orientations, run through the software again to try and come up with a 3D model. And the solutions we came out with, the two solutions, the data is there. If we have a look at the actual models, and unfortunately I couldn't work out how to save the rotating asteroid, which would have been a lot more fun than what these ones are here. The one on the left, you can see there, it's with a position of 210 and plus 47 for the pole angle. The one on the right is 27 minus 33. And we're looking at 4 different views of the model of the asteroid. The one on the right probably is not exactly feasible because we've got the asteroid rotating on its long axis, which is not what you would expect. So under these sort of circumstances, the one on the left is the more probable solution. And having a positive value for the beta would indicate prograde rotation. And having a look at how then this model matches the actual data that we were getting, we can then use that to run through it. And so we can see the one on the left there is the preferred model. Sorry, the one on the left is the preferred model. You can see it more closely matches the observations that we got as compared to the one on the right. So this one I was feeling fairly confident on. It seemed to come out fairly nicely. So we then turn around onto the next one. This is the data that I'd got previously in 2003, 2010. Again, nice clear light curve. The periods that I derived on these two, again, were fairly close. So we observed this earlier this year, and again got a nice clear light curve, but the period was different. And I still haven't been able to quite work out why the period is different. But that gave me some problems when I was trying to do a shape model. Somewhat less than precisely defined. So that was a real hassle. I still went through all the steps, came up with a couple of possible solutions, which gave me this sort of results. It looks fairly nice, but there's nothing you can choose. It's too poorly defined to get anything out of. So this is another one that's going to need more data. My suspicion is the fact that the period is a little bit different is making it difficult to really define the shape model well. And had a look at what the errors were like, and you can see two possible solutions. There's virtually no difference between the theoretical model and the observations. So we can't really decide anything at all about the shape on this one. And then we go to having a look at the third one, Candy. I was interested in this because, being from Western Australia, Perth Observatory, Mike Candy worked it there for many years. He was a good friend of mine. So it was one of the reasons I was particularly interested in working with this one. There's the data that we got in comparing 2005 to 2011. Again, very nice, well-constrained periods. So I was thinking, hey, this is looking good. So then we turned around and did the pole search. And I thought, oh, fertilizer. It was a real mess.
No, one thing it's not.
So we have some fun. I went through it anyway, did the data, did the analysis, came up with two possible models that really don't mean a lot. What I think the problem was with this one is I didn't realize until after I'd done the analysis and was trying to work out what was going on, I had managed to pick 2 times 180 degrees apart in heliocentric longitude. So that was one thing I now realise I've got to add to my criteria. Don't pick them when they're on exactly the opposite sides of their orbits. So that's going to be a next one. So I'll be generous and say those results were doubtful. So it's been fun trying to do it. Clearly there's more data needed, particularly for the last 2, and also for Pollet, next opposition, to try and get some more data to see if I can confirm the shape model that we've got. And then, again, with these other ones, try and see, are we anywhere near reality to them or not? But what I found really interesting in this, it's nice to go one step further than just simply a light curve. What can you actually do with your data? It's been an interesting learning curve, somewhat steep, but it's been fun, and so I've enjoyed it, and I'm looking forward to trying to do some more of this and trying to convince some students that this is actually something that's fun to do. For some reason, they're not quite so keen to spend all night out at the telescope for several nights running when it's in the middle of holidays or something like that. Can't imagine why. So that's what I'll be working on for some more of these. So, as I say, it's been an interesting exercise. As is typical, I'm sure Brian Warner, I think, has said it every time I've been here, more data is needed. So, hopefully we're not anywhere near the trapdoor. Thank you. Any questions?